Yeah, let me start. I guess in this audience, there is really no need to motivate this topic of preferences in AI, but nevertheless, I like to start with this quote, which I like a lot personally, by Bravman and Domschlag, who make this point that compared to this original dichotomic notion of a goal that we all know from more classical AI methods, logic-based approaches, preference formalisms are much more flexible and much more expressive. And this is, of course, very useful in many domains. So just as a motivating example, you may think, for instance, of an AI system in the form of a smart house, or let's say a robot who is responsible for controlling the smart house. And here, the smart house can be in a state that is described, for example, by a set of variables, which can be many. So by a high-dimensional state vector, the temperature outside, the daytime, the temperature in room 1, light room, and so on. Music on or music off, so by a high-dimensional state vector. And it's clear that here we would not only like to distinguish, let's say, feasible and non-feasible states, but the house can be in a more or less convenient state, more or less convenient for the person, for example, who is living there. And then the job of the AI agent should be to figure out what is the, let's say, most convenient configuration for the person living in the house. So states are more or less desirable. The same for many other things and many other items. So red wine, for example, it's not just good and bad red wine, but red wine of different degrees of quality, which a person may like more or less. Also probably depending perhaps on the context in which the wine is offered and so on. So I took this example because I will later on come back to it. This example is connected to a quite well-known benchmark data set in machine learning, the red wine data set. There is also a white wine data set, by the way. And here, every wine in this data set, every wine is characterized by a set of properties. These are 11 numerical properties, such as fixed acidity and the level of alcohol, and so on. So chemical properties, basically. Plus, there is a rating of the quality of the wine on a scale ranging from 1 to 10, 10 being the best quality. So when dealing with preferences from an AI perspective, what do we need to consider? Of course, first of all, there is the question of how to represent preferences in a compact way, and different formalisms for representing preferences have been proposed in the literature. I guess many of them you already have seen during this week. Utility function preference relations, I will also come back to, but also more sophisticated formalisms such as CP networks, which I think Jerome also spoke about, generalized additive models, and so on. Then, given a representation, the next question is, of course, how to do inference, how to reason with preferences. Again, quite a number of formalisms have been proposed in the literature. And also the question, where actually do these preferences come from? So this leads to the question of preference acquisition. Problems such as preference elicitation. I've seen there is also a tutorial on this topic, and preference learning, which is the topic of my presentation here. Preference acquisition is important because you can imagine for complicated problems such as the smart house or so, it will be very tedious, if not even impossible, for a person to manually specify all these complicated preferences that you may state, for example, in the form of a CP network, or also in the form of rules, like, for example, if the daytime is before 10 p.m., and the blind down is equal to 1, so the blinds are down, then for the light room 1, light on is preferred to light off. Yeah. All other things being equal. Yeah. You can imagine there will be many such rules that might be necessary to state, and this cannot always be done manually by hand. Fortunately, preference learning may come to the rescue here. So, for example, the smart house robot may observe how the person living in the house is feeling, perhaps, or what the person is doing, turning light on, off, which might be an indirect hint at what the person likes more or less in a specific context. Also, other sorts of preference information is readily available. For example, on the internet, people are specifying preferences all the time in very different forms. So, for example, just by writing a text review for a book, for instance, or rating items or objects on an ordinal scale, like this famous 1 to 5 star scale, or even more numerically on this tomato meter here, where you can give ratings between 0 and 100, and so on. Often preference information is not stated explicitly, but can be derived from what people are doing and how they are behaving. An interesting example is the analysis of so-called click-through data, where the idea is that you look what a person is doing on the internet, and from this you try to infer what the person likes more and what the person likes less. So here's an example. Imagine somebody searches for the name Daniel Bayer on Google, and then he gets this list back by Google, and you see there is a football player who is called Daniel Bayer, and there is also a professor who is called Daniel Bayer. So they have the same name. Google shows first the football player, and then only on the second place the professor. This is rational to do, probably, because most people are more interested in football than in science and education. But if our user now clicks on the second link and not on the first one, you can directly infer, even if this is, of course, a noisy signal, you can infer that that person perhaps might be more interested in science than in sports or football. Yeah. So preferences of that kind, of course, are quite noisy, but nevertheless, they provide a signal. So here is a little bit of notation I'm going to use later on. So whenever we express preferences, we express them with regard to certain options or choice alternatives. So if A is a set of choice alternatives, which we also occasionally refer to as objects or items, then such choice alternatives can be represented in different ways. This is not unimportant from a machine learning point of view. In particular, we can distinguish an atomic representation where a choice alternative is just identified by the name. So, for example, we could identify a certain wine just by the name, Leonetti Merlot 2017. Sometimes choice alternatives are also characterized in terms of properties. So a common representation in machine learning is in terms of a feature vector, where every choice alternative is characterized by a fixed number of attribute, the values of that attribute. In the red wine example, this could be this 11-dimensional real valued vector with the entries for the different chemical properties, or even more general, we could also think of more structured, more complex representations representing choice alternatives in terms of graphs or sequences or whatever. Yeah. Okay. So how do we, or how can we represent preferences? This is all, I guess, quite well known to you. Again, just to fix a little bit of notation, we can represent preferences in terms of relations. So such a weak preference relation might be defined. A is not worse than B, or is as good as B, denoted by this symbol here. And then from such a weak preference, we can derive a strict preference relation, an indifference relation, and an incomparability relation in the standard way. Yeah, so for example, A is strictly preferred to B if and only if A is at least as good as B, but B is not at least as good as A, and so on. On the more quantitative side, we can also represent preferences in terms of utility functions, numerical utility functions, or real-valued functions, assigning a degree of utility U of A to every choice alternative A. And obviously, such a utility function naturally induces such a preference relation, namely the utility of A is greater or equal. This is the standard order relation on the real number line, U of B, if and only if A is at least as good as B. And the other way around, utility function also induces a complete preference relation again in a very natural way, namely A is at least as good as B if and only if the utility assigned to A is greater or equal the utility assigned to B. And also for the strict part in the same way, and for the indifferent part. Incomparability obviously cannot be expressed by using a utility function, a representation in terms of a utility function. Yeah. There is quite an extensive literature on preference representation. Investigating this question, what types of relations, what types of preference relations actually can be represented in terms of specific types of utility functions. Okay, so now my first question to you. I have a small part of the tutorial with some background on machine learning, just introducing in a very gentle manner some basic notions, speaking a bit about supervised learning, the problem of generalization, and so on. Should I speak about this, or should I just drop it because you are all familiar with the basics of machine learning?
Yeah, please talk a few minutes about it.
What?
Talk a little bit about it. Yes. Please, Eyke, yes, please a few minutes about it, yes.
Yeah, good. Okay. Yeah, so some very basics about machine learning might be useful, because after all, preference learning is of course a specific type of machine learning. So at the core of machine learning, as you may know, is the problem of model induction, by which we mean passing from specific data that you have observed, specific data to a general, though always, of course, hypothetical model that describes the data generating process, or at least parts of this data generating process. So the typical situation is that we have a learning algorithm A, and this learning algorithm is given as input a set of data points, a set of observations. Yeah, let's call them Xi, a finite sample coming from a certain data space X, typically called data points. And then the learning algorithm is supposed to produce as an output a model, which is an element H of an underlying what we call hypothesis space, or sometimes you also say a model class or whatever. So the algorithm, the learning algorithm, is allowed to choose one element of this underlying hypothesis space. And therefore, formally, such a learning algorithm can always be seen as a map from the set of all potential data samples it may observe here, this blackboard B, to the hypothesis space. This is how we can formally see a learning algorithm. Here are two simple examples. You may observe just some realizations of a random variable. This is your data sample, the points here, the blue points. And from this, you induce density function. Yeah, and this is your model. You generalize and you induce a density function. Or here, you observe some data points and you do cluster analysis by fitting a mixture of Gaussians, for example, a Gaussian mixture model. In this way, you generalize beyond the specific examples you have seen. Specifically relevant for us is the setting of supervised learning. And in supervised learning, what is specific here is that the data space comprises one distinguished, let's say, dimension, which is defined by specific target variable y. And the target variable y is, let's say, the variable that we would like to predict given a certain instance x as an input. So the interest here is to learn such a mapping from what we call an instance space x to an outcome space y, or more generally to the set of probability distributions over the outcome space if we are interested in predicting, not predicting in a deterministic way, but making probabilistic predictions, which is often much more reasonable to do. So the X here you can consider as a kind of context. This is the input, or called the instance, the predictor variables. And the assumption is that there is a dependency between the predictor variables and the outcome. And this is what the learner would like to figure out. The hypothesis space then consists of a certain class of such mappings the learner can choose from. Yeah. And again, to induce a hypothesis, the learner is given a set of training data points. And now in this setting of supervised learning, the training data points are coming in the form of such tuples, xi, yi. Yeah. We observe an instance xi, and together with the instance, we observe a corresponding outcome yi. Here is a simple example, medical diagnosis. So imagine our instances are X-ray images of patients, and these X-ray images, they are labeled with positive or negative. This is the target variable. This is a binary classification problem. They are labeled with positive and negative, depending on, for example, whether a certain disease is present or not. And from this training data, via a process of model induction, the learner infers a general model, which could be represented by a neural network, for example, or whatever learning method you apply here. In any case, this model is then, let's say, is generalizing and can be queried with any new X-ray image as an input. Yeah, any new X-ray image that the learner has possibly never seen before, and for which it will then deliver a prediction, either a deterministic prediction or better, a probability distribution by, for example, predicting a certain probability for positive and a certain probability for negative. So what is in general the goal of the learner? The learner, of course, would like to find a hypothesis which makes accurate predictions. And what does that mean? Making an accurate prediction means at least this is how this is commonly formalized, making or finding a hypothesis which has a minimal expected loss. This is also called the risk. And the loss, the expected loss or the risk of a hypothesis is just defined in terms of the expected loss. The L here is a loss function. The expected loss, where the expectation is taken with respect to an underlying probability distribution P, which we suppose is generating the data. This is, of course, not known to the learner. The loss function is comparing the truly observed outcome, the target variable, with a prediction made by the learner. Yeah, and penalizing any deviation between these two. In the case of binary classification, this could just be the 0-1 loss. Yeah, assigning a loss of 1 when the prediction was wrong and of 0 otherwise. For other problems, like regression problems, predicting a real valued outcome, for example, could be the squared error loss or whatever you can think of. So the expected loss you can think of as just the average loss that the learner incurs when it uses this hypothesis H. Yeah, this is what I said already. And then the common, let's say the common target of the learner is to find the so-called risk minimizer, which is the element in the hypothesis space which has the lowest risk among all models it can choose from. So the key question here is, of course, how can such a risk minimizer be found, or at least an approximation to such a risk minimizer? The problem is, as I said, this P here is not known, of course, not known to the learner, and therefore the risk of a hypothesis cannot be computed by the learner. So what can be computed instead is how a hypothesis H is performing on the training data. Yeah, because this is what the learner has at hand, and therefore it can compute the performance or the average loss of a hypothesis H on the training data. This is called the empirical risk of the hypothesis H. Empirical because it refers to the training data. Yeah. And then one obvious idea could be to say, okay, if we cannot compute the real risk, but we can compute the empirical risk, then maybe we could use the one as a substitute of the other and approximate the risk minimizer, the true risk minimizer, the optimal predictor, by the empirical risk minimizer. This is called empirical risk minimization. And the question is that a good idea or not? And in general, of course, the answer is no. It's in general not a good idea because it's quite well known that a small empirical risk of a hypothesis H, this is also called the in-sample error, does not necessarily imply a small true risk, and this is also called the out-of-sample error. So if a hypothesis seems to do well on the training data, it does by no means mean that it will also perform well on new data that it hasn't seen before, that it will generalize well. Yeah, and the generalization performance that is achieved by a hypothesis that is fit to the training data, for example, by doing empirical risk minimization, also strongly depends on, let's say, the expressivity, the richness of this underlying hypothesis space H, which is also called the capacity of that space. Yeah. So especially if the capacity is too high, if you fit a model, for example, which is very flexible, has many degrees of freedom, then there is a tendency to overfit the data. Overfitting means that you achieve a very low in-sample error. So you fit the data, the training data very well, but you generalize poorly. The other way around can, of course, also happen. If the capacity is too low, then the learning algorithm may underfit the data. For example, you may try to fit a linear model to dependency that is actually highly nonlinear, and then, of course, you underfit. Here is a simple illustration of this phenomenon, and let's say the difficulty of generalizing well. Suppose that we produce a certain product, and one thing we can control is the temperature of a machine also. Yeah, this might be this parameter x1 here. And depending on how we choose this parameter, we may end up with a different quality of our product. And now imagine you would like to, let's say you would like to find the optimal temperature. You do some tests, so you try different temperatures here and you measure the quality, which might be, of course, a bit noisy. This quality measurement might not be so easy, might be noisy. And so you have a few data points here produced. So first question, what do you guess? I mean, what will be, for example, the quality when we take the temperature to be 25? So how would you come up with such a guess, with a prediction of the quality for temperature 25? Now, I guess what you are all doing is somehow fitting a function to this to these data points, right? You are generalizing a bit, and then figuring out, I mean, what is the y value of that function at the position 25, right? So who would like to make a guess?
Please say something, some of you.
What? How much?
70.
70? Yes, maybe not bad. Okay, so why is this difficult to answer this question? It's difficult because of the following. So if you now fit a model, you have the choice of what I called the hypothesis space before, the underlying model class. So you could say, for example, I guess that this dependency is linear. So I guess it's a simple dependency between temperature and quality, and you fit the best linear function you can do. There might be this red one here, and you explain the deviations here between your function and the measurements by measurement noise. Maybe your device for measuring quality is not so good. Yeah, and then you end up with this prediction here for 25, and the answer to the question, what is the best temperature, would be 50. 50 leads to the highest quality. Okay, but you may also, now you may start thinking and say, maybe my quality measurement device is not so bad. Maybe this is underfitting the true dependency. So I need a more flexible model class. And you may fit, for example, a quadratic function. This might be the blue one, the best fit to your data. And then you get this prediction here, quality even over 100. And the optimal temperature might be 27 also. Yeah. Or you may even go further and say, oh, I trust my measurement device a lot. And perhaps the dependency is even more complicated. And you fit an even more complicated nonlinear function to your data. And now, again, you get a different prediction for the value at 25, and yet another answer to the question, what might be the best temperature to choose. And you see that depending on the assumptions, the model assumptions you start with, you get quite different predictions and quite different answers to the original question. The data has not changed at all. It's always the same data. You only looked at the data in different ways, and you learned with different, let's say, prior knowledge. And this is only a simple one-dimensional example. Yeah, you can imagine that things become even more complicated when you learn in very high dimensional spaces, which is the common standard in machine learning these days. By the way, how can you now figure out which of these three alternatives might be the best one or the correct one? What will help, of course, is more data. So when you have seen more data, at some point, you will probably be convinced that maybe this blue function here is the best choice. The problem is, of course, you not always have that amount of data at hand. Especially in high dimensional spaces, you really need a lot of data to figure out what might be the best model class to choose from. Okay, so what can you do? One way, to improve this simple idea of empirical risk minimization is called regularized risk minimization, where you try to find a good compromise between the fit to your data. This is the in-sample error, called it in-sample error before, and a complexity of your model. Yeah, this omega here of H is measuring somehow the complexity of your model. The lambda is called the regularization parameter. And what you try to find is a good compromise between fit to the data and complexity of the model, so as to avoid this problem of overfitting your data. Then, of course, the question is, what is a good regularization parameter here? And in machine learning, there have been developed techniques to find a good parameter, for example, based on validation, etc. Another important approach, which is well-grounded in statistics, and to which I will also come back a little bit later in the tutorial, is maximum likelihood estimation. I guess you all know about. This is a method or an induction principle that you can use whenever you are working with parameterized classes of hypothesis spaces. So often every hypothesis is uniquely identified by a certain parameter vector, theta. We then also speak of a parameterized hypothesis class or a parameterized model space. Yeah, so there is a one-to-one correspondence between the hypothesis space and a parameter space theta. And then if we work with probabilistic models, and we fix a parameter vector theta, then the data we observe has a certain probability. Under this assumption that the data is generated by this probabilistic model H theta, the data has a certain probability. The probability of the data given the theta, this is called the likelihood of theta, of the parameter, and the maximum likelihood estimation principle then prescribes to pick that parameter as an estimate theta hat for which the likelihood is the highest, yeah, which, so to say, makes the observed data maximally plausible, under which the data is maximally plausible. So this is a reasonable principle intuitively, but not only intuitively, it also enjoys very good, actually mathematically good statistical properties. Okay, yeah, so this I don't necessarily need. What you typically do is, yeah, actually this is even needed most of the time, that you make an IID assumption. You assume that the data points you observe, the different training examples, are independent and identically distributed, and then the likelihood, the probability of the data given your parameter can be written as a big product. which you can then which you then have to maximize. And instead of maximizing a product, which can be quite complicated, it's better typically to maximize the log of the product, which is the sum of the logs of the probabilities. A sum is more easy to handle, especially when taking derivatives. Yeah, often these optimization procedures, maximization procedures are based on gradients, and you know that taking a gradient of a big sum is quite troublesome. Taking the gradient of a big product, taking the gradient of a sum is easy because it's the sum of the gradients. Okay, and Bayesian learning, just as a side remark, can be seen also as regularized generalization of maximum likelihood estimation, where we start with a prior distribution, which can be seen as a kind of regularizer. So there is a connection also to this method of to this approach of regularized risk minimization that I mentioned before. Okay, good. So this is a very short background on machine learning and this key problem of generalization. So what I would also now like to do is to speak a little bit about rankings and probability distributions on rankings. And I'm doing this because rankings are playing a very important role in preference learning, because preferences are often represented in terms of rankings there, which is a specific type of preference relation. And as you have seen also now in this short introduction, probabilistic modeling plays a very important role in machine learning. This is because in machine learning, we always assume that the data we observe might be noisy, that this dependency between X's and Y's, between instances and outcomes is not necessarily deterministic, but might be probabilistic and so on. So probabilistic modeling and statistics is very important in machine learning. And here, these two things are now connected with each other. Probabilistic modeling of preferences, if you want. So what I mean by a ranking is strict total order. So it's a total, irreflexive, and transitive order of choice alternatives. So if we have a finite number of choice alternatives, let's call them A1 to AK, then a ranking is putting them in an order, in a linear order. We can always identify such a ranking with a permutation, which I denote by pi, a permutation of the set of numbers 1 to k, which is abbreviated here by this bracket k. So it's a bijection on this set of numbers from 1 to k, where by convention, pi of k denotes the position of the kth choice alternative in the ranking, meaning that pi of I is smaller than pi of j if and only if the alternative AI is preferred to the alternative AJ. The inverse is sometimes also called an ordering. So inverse pi of j equal to I means that the choice alternative AI is just put on the position j. So basically, so then with this inverse, the ranking looks like this. Now, this is the best alternative with the index inverse pi of 1. This is the second best, and so on. So we denote the set of all rankings on such a set of k choice alternatives by Sk. S is standing here for symmetric group. So this is the symmetric group, basically of order k, which, by the way, has an interesting topology. This is shown here for the case k equal to 4. So you see every node here corresponds to one ranking of 4 alternatives. and two rankings are connected with each other here by an edge, if and only if the one ranking can be obtained by one swap of two adjacent elements. Yeah, so you see, it's an interesting topology, also interesting from a machine learning perspective as a target space in which you perhaps want to make predictions, because the space is on the one side finite, like in classification problems, but on the other side, typically quite large because the number of rankings is k factorial, and also a space which, as you can see here, has an interesting topology. So it's not just discrete space with no or discrete topology, but it has an interesting topology. So a natural neighborhood relation also. What we need in machine learning is a notion of distance, because this is directly connected what I called loss before. If we want to predict, for example, rankings, and we would like to evaluate, assess a prediction, then we need a notion of distance or loss. Distance measures on rankings have been proposed a lot in the literature, and there is a close connection between distance measures on rankings and so-called rank correlation, which you, I guess, have heard about. So if you have two rankings, the question is how well do they agree with each other in terms of the ordering? This is typically captured by the notion of a correlation. A common relationship between correlation and distance is given by this expression here. In many cases, we have that correlation between two rankings pi and pi prime is equal to 1 minus twice the distance between these rankings divided by capital M, where capital M is the maximal distance, which of course always exists because the space of rankings is finite. And you see here that this value ranges between -1 and 1, -1 and +1, -1 typically corresponding to the case of perfect anti-correlation. You reverse the one ranking to obtain the second one, and 1 meaning perfect correlation, so pi is equal to pi prime. Two important examples from the literature is Spearman's rho, which is this correlation measure here, which is simply a linear or an affine transformation of what is called the Spearman distance. And the Spearman distance between two rankings, pi and pi prime, is just the sum of the squared rank differences. So you look at every choice alternative I, what is the position of I in the one ranking, what is the position of I in the other ranking, and you take the squared difference between the two and you sum overall k alternatives. Another a related measure is called Spearman's foot rule, which is similar, except that you do not take the L2 norm here, but the L1. You sum up the absolute differences between the positions in the two rankings. This is a distance measure called Spearman's foot rule. Another important case is the Kendall distance. What Kendall is doing is defining distance in terms of the number of discordant pairs of items or choice alternatives. Discordant means that the two are ranked in different order in the two rankings. So if the order is the same, then the pair ij is called concordant. So either in both rankings I is better than j, or in both rankings j is better than I, and otherwise it's called the pair is called discordant. And Kendall distance is just defined in terms of the number of discordant pairs of items. And this is related, again, to a correlation measure, which is called the Kendall's tau. And this is, again, a rescaling of the distance to the interval -1, 1, given by this expression here. +1 for identical rankings and -1 for reversed, and everything in between, taking values between -1 and 1. Okay, so as I said, when we would like to do machine learning in general or preference learning in particular, we typically deal with probabilities, yeah, and do some sort of statistics. This is why it's quite convenient to have probability distributions on rankings. More specifically, what we might be interested in is a distribution, a probability distribution P, which assigns a probability to every ranking of a set of K choice alternatives. So which formally is such a mapping from Sk, the set of all rankings of length K, to the unit interval, such that, of course, the sum of probabilities is equal to 1. Otherwise, it's not a proper probability distributions, and the values P of pi are non-negative. Yeah. P of pi here is the probability assigned to the ranking pi. Yeah, so what might be a bit tricky here, if you would like to specify such a probability distribution, what might be a bit complicated is, of course, that the space here, as I said before, is quite large. The number of rankings we have is K factorial. So for very small numbers K, you might specify such a distribution in tabular form by hand if you want, but for larger values K, this is of course not possible anymore. And this is why parametrized families of distributions on rankings have been proposed in the literature, and I will show you one of them on the, not the next slide, but the slide after, which has attracted quite some interest also in machine learning, because it's a quite convenient family of probability distributions to work with. Before I introduce this model, let me just mention that, of course, when given a probability distribution on Sk, we can, of course, extend this distribution to all incomplete rankings. This TOR here is supposed to be an incomplete ranking, incomplete meaning that it's a ranking of a subset of the options A1 to AK. Not all of them, perhaps, but some of them. And then the probability of such an incomplete ranking is simply obtained. This is, probabilistically speaking, an event that we observe, is given by the sum of the probabilities of all pi which are compatible with this incomplete ranking tau, in the sense that they belong to the set of linear extensions of that incomplete ranking. So here is a simple example. Suppose we are given a probability distribution P on 3 choice alternatives, then the probability that A1 is better than A2, yeah, is simply the sum over all, the sum of the probabilities of all rankings in which A1 is better than A2. And in this case, you see it's 3. Yeah? These 3 possible rankings are linear extensions of this incomplete ranking. Here it's a quite small number, but you can imagine that if the K is larger, then computing such a sum here can be a quite tedious thing to do. Yeah, and we can generalize this, of course, for every subset J, for every subset of choice alternatives J, in this way, by summing over all linear extensions, you can define a probability distribution on this subset, which is called the marginal distribution on this subset of choice alternatives J. Yeah. So in particular, this includes the case of pairwise marginals. Like the example we have just looked at, we can compute for every pair of choice alternatives AI, AJ, we can compute the probability that AI is preferred to AJ. Now, when we generate a ranking at random according to our probability distribution, what is the probability that in this randomly generated ranking, AI precedes AJ? Now, this is what we call PIJ here, and this is something I will also come back to a little bit later. So now this model that I already announced is called the Plackett-Luce model. Maybe some of you heard this name already. The PL model is a parameterized model, a probability distribution, which is parameterized by such a vector theta with one entry for every choice alternative. So if we have k choice alternatives, we have k parameters, theta 1 to theta k. These are all non-negative, and the theta I can be interpreted as something like the weight or the strength of that alternative AI. So the higher the theta I, so to say, the better, the more preferred the choice alternative is, or latent utility, if you want, you can interpret. And given this parameterization, the distribution itself is defined in the following way. The probability assigned to a ranking pi under this Plackett-Luce model with parameter theta is given by this expression here. And this expression is a big product, as you can see. And at first sight, when you see it for the first time, you may not immediately see what's going on or see why this is maybe a reasonable expression, a reasonable way to assign probabilities. But this product actually is quite simple to understand. Here I have an illustration which makes it, I guess, quite clear. So you can illustrate the Plackett-Luce model by an urn model, which is shown here, where you can think of this weight here, the theta I, as the proportion of elements of balls, let's say, inside the urn, marked with the corresponding choice alternatives. So here we have three alternatives: green, red, and blue. Green has the highest strength. We have 10 green balls in the urn, 6 red balls, and 4 blue balls. And then how is Plackett-Luce computing the probability of a ranking? So for example, the ranking first red, then green, and then blue. The probability of that ranking is obtained as follows. The idea is that you generate a ranking in a stage-wise manner, where you first choose the first object. So you first place, you first select the top alternative, then the second best, then the third best, and so on. At every time you choose the next best element, the probability that you select a specific element is proportional to the strength of that alternative. So what is the probability that we first pick a red ball? It's 6/20, because we have 20 balls in the urn. and 6 of them are red. Then the next element, what is the probability that we choose green? As the next element is 10 over 14. We have 14 left if we remove the red ones, and 10 of them are green. And then, of course, only blue remains. So the probability that blue is ending up on the 3rd position is 1. And this is the value we obtain. The probability of this ranking is 3 over 14. This is the big product you have seen on the previous slide. And you can compute this value for every permutation, and you can also formally verify that this is defining a proper probability distribution, namely the sum of all these probabilities is equal to 1. And you also see that the higher the theta I, the higher the probability that the corresponding choice alternative will end up in a top position. Okay, so and in particular, you obtain the mode of the Plackett-Luce model, the ranking which has the highest probability, just by sorting the elements according to their theta parameters, according to their weights. The one with the highest weight first, then with the second highest, and so on. What is very convenient for the Plackett-Luce model is that every marginal distribution, so every distribution on a subset of the choice alternatives, is again a Plackett-Luce model with the same parameters they had before. You remember on one of the previous slides, I showed you this big sum that you actually have to compute in order to project to a marginal. Here you don't need to do any computation, I mean any summation, because every marginal of a Plackett-Luce model is again a Plackett-Luce model. This is a very nice property which is not shared by other probability distributions on rankings. In particular, the pairwise probabilities are called the Bradley-Terry probabilities, and the probability that AI is preferred to AJ in a randomly chosen ranking is simply given by this expression here, theta I over theta I plus theta J. A side remark, the Plackett-Luce model is actually the unique model that has nice mathematical properties. In particular, it follows from the Luce choice axiom, which I guess many of you heard about, which is postulating this independence of irrelevant alternatives properties. So the preference between any two items must not depend on the presence or absence of any other choice alternatives. So it's very tightly connected to this Luce choice axiom. Also, as a side remark, the Plackett-Luce model is a special case of what is called a random utility model, a RUM, in the literature. And in a random utility model, the idea to define a probability distribution on rankings is the following. With every choice alternative, you associate a certain probability distribution on the real number line, so a real valued probability distribution. And then you generate a ranking by first sampling independently a value, let's say a latent utility value for every choice alternative, and then you rank the alternatives according to these realizations. So here, for example, you would end up with the ranking A3 is first because it has the highest value, and then A1, and then A2. Yeah, and the Plackett-Luce model is obtained as a special case of these random utility models when these distributions here, these random variables U, when these are Gumbel distributions. Yeah, but if you want, you can take any other distribution here, and then you will have different families of probability distributions on rankings. Okay, so now I think it's time for the break, right?
Yes.
It fits quite well because now I'm coming to the to the main part, for which 1 hour might be tight, but I will do my best after the break. I will probably have to skip a little bit, but I hope it was informative for you so far. Okay. So let us continue. Now I'm actually coming to the main part of the tutorial, and since I was cut down from 3 to 2 hours, I will probably have to skip some parts. But I don't think it's so bad. Actually, I will decide dynamically probably where to skip a few slides. So what I would like to do in this part is to present a list, let's say, of important types of preference learning problems that have been tackled in the literature. And to do so, I would like to at least try, let's say, to put them in a kind of unified framework. So let me start with introducing a general setting so that each of these problems we are going to speak about later on can be seen as a special case of this more general setting. So let us consider a scenario in which we observe preferences on choice alternatives, and I will also call them objects or items, as I already did before. And these preferences can be context dependent. This is important in machine learning. We often observe preferences specific to a certain context. So depending on the context, the preferences may change. And these preferences are expressed in terms of utility functions, which might be latent. So we may not directly observe these utilities, but perhaps only some signals, some hints, giving us an idea of how these probabilities may look like. So simple example, a context could be a person, and the objects over which we express preferences might be movies. And then it's clear, depending on the context, if you change the context, if you change the person, the preferences over movies may also change. We are going to denote these contexts by X and the items or objects by Y in the following, following standard, more or less standard machine learning terminology. And the corresponding spaces by this calligraphic X, calligraphic Y. These spaces of contexts and items, they may or may not have a representation in terms of properties. As I said before, this is always important from a machine learning point of view. If they do have a representation in terms of properties, or what we call feature vector, in machine learning, we will denote them by this boldface X and boldface Y, and otherwise just by normal font X and normal font Y. Yeah, if the representation is atomic. We make the assumption that there is a ground truth utility for every pair X, Y. So the utility of the choice alternative Y in the context X, even if we normally cannot directly observe this utility. What we observe is some hint, some information about these utilities, which might be noisy or approximate, for example, if it's expressed on an ordinal scale, or also indirect, if, for example, expressed through just qualitative comparisons, as we will see in the following. So you can imagine a scenario like this, where we have the contexts here on the one side, the axis, and the choice alternatives, the items on this side here, the Ys. And at training time, we observe a certain subset of contexts, and we observe a certain subset of items. This is what the learner sees at training time. So it has seen, for example, a certain number of people rating a certain number of movies. At prediction time, the learner may also be queried with new contexts it has never encountered so far, and perhaps also with new items, a new movie, for example, a brand new movie, which it has never seen before. And you can imagine that making predictions here in the middle is somehow easier than making predictions here or making predictions here, where new contexts are encountered or where new items are encountered. And this region here is probably the most difficult one, where the learner is supposed to make a prediction about utilities referring to a new context and a new item, choice alternative it has never seen before. This is related, by the way, to what is called few-shot or zero-shot learning in machine learning. Yeah, so this is the assumption that these capital N contexts and the capital K items have been observed at training time. They have been seen at least once by the learner, and the others not. Okay, so as I said, these problems we will look at can be seen as specific instantiations of this general setting. The problems have these instantiations have different characteristics. For example, regarding the question about representation, the contexts and the choice alternatives, are they represented in terms of properties or not? You can imagine that if you want to generalize to new contexts or to new choice alternatives, this is essential, yeah, that you have properties. Otherwise, there is no chance to generalize if the representation is atomic. The type of supervision, so what information is provided to the learner about preferences? Does the learner observe utilities? Does the learner observe qualitative preferences, and so on? The type of model the learner is supposed to produce and the type of model we actually would like to obtain. Is the learner supposed to predict numerical utility degrees, or is the learner supposed to predict rankings, for example, etc.? And also the type of performance metric that is supposed to be optimized. I used this notion of a loss function before, you remember. So how is a prediction penalized, and what should the learner do to perform best in terms of the performance metric it is actually evaluated with? These preference learning problems that have been studied in the literature are quite challenging sometimes from a machine learning perspective, especially because, first of all, the supervision is often relatively weak, as we will see in the examples we will look at. At the same time, the predictions that are supposed to be delivered by the learner can be quite complex structures, such as order relations, rankings, order relations, and so on. And the performance metrics might be relatively hard to optimize. So if the learner, for example, is produced to perform well in terms of ranking, where accuracy is measured in terms of Kendall tau, for instance, that might be relatively hard to optimize. In general, one can distinguish a couple of different machine learning techniques with which preference learning problems can be tackled, and I just wanted to summarize them here, give a short overview. One way to go is to try to learn the underlying latent utility functions, yeah, which may depend on the context and the choice alternative, or if the context doesn't play any role, only on the choice alternatives. These latent utilities, which we assume to exist, even if they cannot be observed directly, are real numbers, and therefore the idea of learning these latent utility functions is very close or naturally leads to problems of regression from a machine learning perspective, real valued functions. Another way to go would be to learn preference relations. You remember there are two basic ways of representing preferences in terms of numerical functions and in terms of binary relations. And we may also think of learning binary relations, yeah, which take as an input two alternatives, A and B, and decide whether A is preferred to B or the other way around. And this naturally leads to classification problems from a machine learning perspective, because here a distinction is only made between two choices, yeah? Positive, negative, A better B, B better A. What one could also think about is to leverage methods for so-called structured output prediction, which have been developed in machine learning, and where the idea is that one trains a predictor which predicts a complex structure, a sequence, a graph, or whatever, in one go, so to say, in a holistic way. And such techniques can be used in preference learning and have been used simply because preference structures like rankings and so on can be seen as a special case of structured objects of that kind. Yeah. Therefore, structured output prediction can also be used in the realm of preference learning. Then what I call model-based preference learning, this is not necessarily a very common terminology maybe, but I think the term fits quite well. This refers to methods which proceed from specific models or assumptions about the type of preference structures to be learned, so which from a machine learning perspective have a relatively strong representation bias. And by these models, I basically mean models that have been developed by people in the decision sciences, so in multi-criteria decision making and so on. Very interesting models have been proposed to represent preferences. Maybe you heard about the Choquet integral already. I'm pretty sure you did. The CP networks I mentioned already, and so on. And the idea would be to induce models of this kind, which have nice properties, can be interpreted intuitively, and so on, in a data-driven way. Yeah, so to combine, so to say, preference modeling and machine learning. This is what I mean by model-based preference learning. And this is, let's say, a parametric way of learning, because these models are typically identified by a certain number of parameters. And what can, of course, also be used is, let's say, nearest neighbor type of learning methods. I call local preference aggregation here, which has the advantage that there is no need to represent any complicated preference valued type of function also, yeah. Where you just look at, let's say, similar cases you encountered in the past and then transfer the preferences, or for example, the preference relation you observed in that context to the current context, because the context, for instance, seems to be similar. Okay, this is a very broad categorization. So here you see the list of methods or problems, actually, I would say, which I wanted to go through. Probably I won't make it, as I said, but let's see. What I would like to start with is maybe the simplest instantiation or the most obvious instantiation of this general setting that I introduced, which is the problem of matrix completion. And I guess you already heard about, because I've seen there was another tutorial about recommender systems, and I'm pretty sure that was mentioned. Therefore, I will only mention it briefly here. So what I mean by this problem of matrix completion is the following. So let us assume, again, we have this set of contexts that the learner has observed at training time, x1 to xn, and a set of items, y1 to yk, which are atomic, so which have no specific feature representation. Might be, for example, just people identified by the name, and movies also identified by the name or any other sort of product. And we observe utilities, uij, for some, but typically not all combinations of ij. For example, some users have rated some movies. Yeah, this is a standard setting you encounter in applications such as collaborative filtering. Yeah, you observe sparse metrics like this here, and then the goal actually is to fill these metrics. This is why it's called metrics completion. It's a problem, as I said, mostly studied in the realm of recommender systems, but I think one can also see it as a special case of preference learning, because after all, these entries here, like 1 to 5 stars or so, are typically interpreted as probabilities. So the question is how to tackle this problem, how to fill such a matrix in a reasonable way. So we would like to have here a full utility matrix, capital U, without, however, going beyond these contexts we have seen during training, and also not going beyond the items we have seen during training. So for collaborative filtering, there is a huge number of methods that have been proposed in the literature. In one way or the other, they all follow the following assumptions, namely, if two users or contexts have rated many items similarly in a similar way, then they will probably also rate other items in a similar way. So what these methods are mostly looking at is user similarity, yeah, with the idea that you figure out a similarity between users, and then if two users are similar, the one has rated a certain product, the other one did not, you can hypothetically transfer the rating of the former one to the latter one. As performance measures, different metrics can be used. What one typically looks at is the average absolute distance between the predicted entries of this utility matrix and the true entries, or the Euclidean distance between them, or whatever. So just very briefly, there are two ways in which this problem could be tackled. The one is so-called memory-based methods. Memory-based methods try to estimate, as I said before, the similarity between users, and then derive predictions in terms of weighted averages where the weight is proportional to similarity. Here you see a toy example showing a certain pattern. If you look at here carefully, or actually you do not even need to, because I highlighted already in colors, you may figure out that there seem to be two groups of users and two groups of items, so that the one group of users, x1, 4, and 5, seems to like, because they give high ratings, to the first group of items, for example, movies, and low ratings to the second group, and just the opposite for the second group of users, x2, x3, yeah, rating the first group of items low and the second group high. And patterns of this kind can be used then to hypothetically fill the the missing entries in this utility matrix. Another approach, a little bit more principled perhaps, is matrix factorization. Probably you also heard about in the other tutorial. Here the idea is to approximate this utility matrix U in terms of the low rank approximation. So we are looking for a so-called K-factor model where we represent or let's say embed every context in a K-dimensional Euclidean space. So represent every context by K latent features, and the same for the choice alternatives, such that the utility matrix is close to the product of X and Y. So this can be seen also as a generalization of standard linear regression techniques. So this is shown here. We assign such a feature vector to every context and also to every choice alternative in such a way that if we multiply the two, we approximately end up with the utility here. With those utilities we have observed at training time, and then of course once you are given this latent feature representation, you can generalize and also make predictions for others for other cells that the learner did not observe at training time. Okay, so matrix completion, if you want, can be seen as a special type of preference learning and a specific instantiation of this framework I introduced. So then what has received also a lot of interest in this field of preference learning is ranking methods. Yeah, and these three here, which are now following, are all different types of ranking problems. There are even more, but I think these are perhaps the most common or the most important ones. The first one is called learning from label preferences, or also label ranking, the task of label ranking. In this task of label ranking, the contexts are characterized by properties, typically in terms of feature vectors, whereas the choice alternatives, the items, are simply encoded by their names. So they have an atomic representation. Again, this is important from a machine learning perspective. The number of items is typically moderate, low to moderate, I would say. We have capital K different choice alternatives, and in this context, they are also called the labels. This is why the problem is called label ranking. Yeah, and the assumption is that we have seen them all at least once at training time. With every context, we associate some sort of ground truth ranking of the labels, and information about some rankings for some context is provided as training information, even if the observed rankings are not necessarily complete. So it can also be partial rankings on only a subset of the choice alternatives. And also these observations might be noisy. So there might be observation mistakes or whatever sort of noise in the data. So here is a simple example. Suppose that the context is a person characterized by the age, the gender, I don't know, the yearly income or whatever. Properties, socio-demographic properties, for instance. And the ranking is a ranking over different social media things. How are these called? Platforms. Yeah, social media platforms, maybe. Like, oh, what is that? Is this Instagram? I always, Instagram, Facebook, Twitter, TikTok, and I think this is Snapchat, right? I'm not a big specialist these things, but I think these are the names. So this person likes Instagram the most, or uses Instagram the most. The second best is Facebook, and so on. This could be the ground truth ranking for that person. And other persons, of course, have other rankings. So then how does our learning problem look like? We observe training data of this form. We observe instances xi together with rankings pi I, which might be partial. This is why I put a bar here on this sk. These rankings are not necessarily complete, might be also rankings of only a subset. If you ask a user, for example, he may say, I like Facebook more than Snapchat, but doesn't tell anything about the other social media platforms. Given training data of that type, what we would like to learn is a hypothesis which is a mapping from the instance space to the set of all rankings over the k choice alternatives. So which takes any new person, for example, with any new properties as input, and then predicts a complete ranking over all the choice alternatives. Yeah, at least as good as it can. As usual in machine learning, we penalize such predictions in terms of a loss function, L, which compares a predicted ranking with a ground truth ranking. And the interest of the learner is to produce a hypothesis which performs well on average in expectation, so which has a low loss in expectation. Yeah, the loss could, for example, be the candle distance between the two rankings, which we introduced before, but could also be any other sort of loss function on rankings, or distance measure on rankings. Now, so the situation looks like shown here. The black part here is the training data. Yeah, for the first person with these properties, the learner observes this ranking here. For the second person, only partial information. Snapchat better than TikTok, Instagram better than Facebook, and so on. And given this as training information, the goal is to learn a predictor which for any new person with any new properties is able to predict a complete ranking over all the different choice alternatives. So how can this problem be tackled? Different methods have been proposed for label ranking in the literature. One way is using this Placket-Loose model that we introduced before. And this is a quite interesting approach, I would say, because this Placket-Loose model does not only deliver predictions, but even probabilistic predictions. So even information about how certain or uncertain the learner is about a predicted ranking, for example. So how can the Placket-Loose model be used in this context of label ranking? You remember that the Placket-Loose model is a parameterized model where every choice alternative has a certain strength. Yeah. Now in label ranking, the strength or the preference for certain choice alternatives is actually contextualized. Yeah, because depending on the context X, the choice alternative, for example, the preference for Facebook, may differ. And here, therefore, the idea, therefore, is that we do not fix these parameters of the Placket-Loose model as constants, but we allow them to be a function of the context. Yeah, we express them as a function of the context. In the simplest way, for example, in a log linear way, namely as the exponential of the inner product of a weight vector, Wi, which is specific to the i's choice alternative, and the vector, the feature vector of X. Exponential to make sure that the values are non-negative. You remember for the PL model, we must assure that these parameters are non-negative. Yeah. So the parameters of this model are now W1 to WK. if we have k choice alternatives, we have one weight vector for every choice alternatives. We can summarize these weight vectors in a big matrix W, capital W, and then we can compactly express the model in this form here. The parameter vector theta is the exponential of W times the feature vector X. Yeah, so in our social media platform example, this may look as follows. We make the assumption, for instance, that the latent utility for Facebook is given by the exponential of this linear function here, a coefficient W Facebook 1 times the gender of the person plus another weight W Facebook 2 times the age of the person and so on. And the same for the other choice alternatives. Now, to learn, learning a predictive model now comes down to learning these parameters here, right? These W parameters. And this we can do by, for example, leveraging this idea of maximum likelihood estimation we know from statistics. And we can look for that W parameter or parameters for which the likelihood of the ranking information that we have observed in our training data, the probability of these observed rankings becomes maximal. Yeah, so we maximize the likelihood of this W, of these W weight vectors. Yeah, this is what you can do. And formally, the problem then looks like this. Yeah, we try to find those W vectors for which the likelihood of the observed data becomes the highest. So we end up, as usual, when doing maximum likelihood estimation, we end up with a maximization problem, an optimization problem. And as you can imagine, this is a quite complicated problem, not easy to solve, especially because this function is highly nonlinear in these W vectors. Yeah, if you plug in for this probability, this Plackett-Luce formula expressing the probability of a ranking, you remember with this big product, then you can imagine it becomes a quite complicated function. The good news is this function is still convex in the W vectors. So you can use convex optimization techniques here, and such techniques have been used in the literature. There are good algorithms for solving them iteratively. Of course, there is no closed form solution, and using such methods, we can come up with an estimate of these W weight vectors, and therefore, given an X, we can come up with an estimate of these theta parameters of the Plackett-Luce model, and then produce a prediction of the ranking for a given X, a ranking pi hat by sorting the choice alternatives according to their estimated parameters. Yeah, this is the mode of the Plackett-Luce model. And the good thing, as I said, for Plackett-Luce is we do not obtain only a prediction of a ranking, but actually we obtain a probability for every possible ranking, yeah, which is often quite convenient to have. Okay, so this is this label ranking problem. Another important type of ranking problem is called, sometimes called object ranking, sometimes it's called learning to rank. Is learning from object preferences, and the important difference here is the important difference to label ranking is the following. First, the choice alternatives that we now try to rank are characterized in terms of features, unlike the case of label ranking, where they are just identified by the name. Here, every choice alternative has a feature representation. For example, imagine we would like to learn to rank red wines characterized in terms of these 11 chemical properties. There is no context now. So in this standard LTR learning to rank setting, there is no context, but the choice alternatives are now characterized in terms of feature vectors. The task of the learner is to learn a ranking function, R, which accepts any subset of choice alternatives as an input. So, for example, any subset of red wines you may think of, and then provides as a prediction a ranking of this subset of objects. This is what we call a ranking function in this context here. Training information consists of either example ratings, exemplary ratings. For example, you may observe utilities or quality degrees for different red wines. Somebody may tell you this red wine has this quality level, that red wine has another quality level, and so on. Or we observe pairwise comparisons. This is also a case commonly encountered in practice, like I like this red wine more than that red wine, or perhaps even rankings of larger size of a subset of objects, like given these 3 red wines, I like this the most, this the second best, and that the third best. Correspondingly, given these different types of training information, a distinction has been made in the literature between so-called point-wise learning methods, relating to the example rankings here, pairwise learning methods, when the data is coming in the form of pairwise comparisons, and list-wise, so-called list-wise learning methods, when the training data comprises rankings of a longer size. So again, to fully specify machine learning tasks, we also need a performance measure, which needs to be targeted by the learner. The learner should try to perform well in terms of a specific performance measure. And this is specifically interesting in the case of object ranking, because in this learning to rank problem, often the number of items that we would like to rank is relatively large. Learning to rank is also commonly used in information retrieval, where the choice alternatives are documents or websites, for example. Google also has the problem of ranking websites given a query and so on. This is also also a ranking problem. And then given a predicted ranking and a ground truth ranking, the question is how good is the one in light of the other one. Once again, we could use distance measures on ranking as we introduced before, such as Kendall and Spearman. This is possible, but especially in this context, if you think again of this information retrieval scenario, Google and so on, these measures have one important disadvantage, namely they assign the same importance to every part of the ranking. So if you swap, if you swap 2 elements at the bottom of the ranking, it's as bad as swapping 2 elements at the top. This is not good, because in such contexts, we are often much more interested in the top positions than in the bottom positions, and therefore we would perhaps like to use performance metrics which penalize mistakes in the top more than mistakes in the bottom of a ranking. And such measures have been developed, especially in information retrieval. For example, maybe you heard about a measure called the NDCG, the normalized discounted cumulative gain, which is quite complicated measure, and so on, which I'm not going to introduce here. I just wanted to make this point that such performance metrics are used, and from a machine learning perspective, these measures are hard to optimize. So for the learner, it's not easy to, let's say, learn to perform well in terms of these metrics, because these metrics are often non-convex and mathematically not easy to tackle. Okay, but this only as a side remark. Now, coming back to this basic distinction between point-wise, pairwise, and list-wise learning methods, I will try now to skip a little bit the details, because otherwise it takes too long. But let me try to at least convey the basic idea. So, as I said, by list-wise learning methods, we mean methods that are where the learner is trained on exemplary ratings. So the learner is trying to learn a latent utility function, assigning a utility degree to every choice alternative. So let's call this utility function F, assigns a hypothetical utility degree to every choice alternative in this set calligraphic Y, where the utility function is typically a real valued utility function, or maybe utilities restricted to a bounded domain, such as the unit interval, and sometimes, of course, also an ordinal utility scale, like this common 1 to 5 star rankings that we often observe in practical applications. If the learner manages to learn such a latent utility function F, then the ranking problem can actually be reduced to a scoring plus sorting problem, because what the learner will do, given any subset of choice alternatives as an input, for example, a new set of red wines, the learner will hypothetically score every choice alternative in terms of this learned utility function, and then sort the alternatives in descending order of the predicted utility UI head. Yeah, this is what the learner will do. So such a learned utility function immediately induces also a ranking function, as we would like to have. If we are given this point-wise training information of this form, so here you have, for example, a red wine, and the utility of that red wine is UI, and several examples of that kind, then from a machine learning point of view, the problem is actually a regression, or maybe an ordinal regression problem. So nothing specifically perhaps interesting from a machine learning perspective. Essentially, the problem can be reduced here to standard regression or ordinal regression methods. We may, for example, simply train a neural network, as shown here in our example of red wine ranking, which takes a red wine as an input, for example, in this 11 chemical properties, and then produces a predicted utility degree in this range between 1 and 10 as an output. Yeah. This is then a standard regression problem. However, this point-wise numerical information about these utilities, UI, is of course not always available in practical applications. Often we only observe or derive comparative preference information of the form, the one alternative was better than the other one. So yi is at least as, or is better than yj, for instance, yeah. Such information can be extracted, for example, in this information retrieval scenario from this click-through data that I mentioned in the beginning. Yeah, a person, for example, when looking at Amazon, the person clicks on one product but not on another one next to that product, and then you can infer maybe the one was more attractive than the other one to that user. So if we observe such a pairwise preference, yi is better than yj, then, and we are still interested in learning such a latent utility function f, then such preference obviously gives rise to a constraint for this utility function, because it is actually suggesting, although it might again be noisy, it is suggesting that the utility assigned to yi should be greater, yeah, should be greater than the utility assigned to yj. This is what such a preference is actually suggesting. So now the challenge for the learner is to find a utility function which is at least as much as possible in agreement with a set of constraints which are imposed by pairwise observations of that kind. So for this problem of learning to rank, this idea has first been formalized quite early. At that time, there was nobody speaking of preference learning, at least not using this term, but at this time, researcher called Tesauro, I'm not sure exactly how to pronounce that name correctly, but he invented quite a very neat method actually for doing this, which is called comparison training, which is inducing such a latent utility function from pairwise comparisons using a specific neural network architecture. And he was doing this in the context of game playing. So what he was comparing was end positions in chess. The one is more promising than the other one. This was what he was interested in. So here, the training examples, this is now a reduction in a sense to a classification problem. The training examples are of this kind. The input to the neural network is a tuple, yi, yj, and then a signal which is either negative or positive, depending on yi is better than yj or the other way around. Yeah, and what Tesauro proposed was such a neural network architecture, which is actually consists of two sub-neural networks, which are symmetric in the sense that they share the same weights. W1 is the set of weights of these edges are the same as here. This is called weight sharing. It's still a technique very much used today. And here, these weights in the upper part are asymmetric. The W3 is minus W4, and the outcome here is supposed to be -1 or +1. And then after this network has been trained on pairwise comparisons, the nice thing is that you can forget about the one part and only use the other part here, the one side. So you can collapse into a single neural network, which then represents your utility function. Yeah? So this was quite a nice idea. And similar things have now been done more recently more recently with other types of machine learning methods, for example, support vector machines, for which the problem of learning such a latent utility function also has been reduced to classification problems. You know, support vector machines can be used for binary classification, and especially if this latent utility is linear, then such a constraint that the one utility should be greater than another one can easily be transformed, thanks to the linearity of the inner product, into a requirement of this form here. And the difference between the two feature vectors you can then consider as a new feature vector, a training example for a binary classifier, suggesting that this training example here is a positive example and the inverse is a negative example. So again, you can reduce the problem of learning such a latent utility function to binary classification, and using kernelization. What is commonly done for support vector machines and other kernel-based machine learning methods, kernelization, you can then also go beyond linear utility functions and learn nonlinear utility functions. So here the problem is finally reduced to binary, again, to binary classification. Yeah. And finally, these list-wise methods, here, the idea is that the learner observes as training information, not just pairwise comparisons, but longer rankings. And instead of cutting them into pairwise comparisons, which may come with a loss of information, the idea would be to use the observed rankings directly. Yeah. This is called listwise learning, or has been introduced under this notion of listwise learning. And what can be used again here is this Plackett-Luce model that we already know, again in a parametrized form. So so the idea here is that now the Plackett-Luce parameter, the strength associated with a certain choice alternative y, is a function of the properties of y. And it could be, again, for example, such a log linear model where we assume that the latent strength of the choice alternative y is a linear function, where the theta vector here, the theta vector, is assigning weights to the different properties. For example, the level of alcohol of a red wine could be an important property for the quality, and therefore the level of alcohol in this weight vector receives a high weight. So the learning problem, then I will quickly go over this. It's a bit too complicated to explain in detail. You can again, like we have seen in label ranking, leverage this idea of maximum likelihood estimation and try to learn the parameter vector here, the theta, for which the observed data has the highest probability. So you maximize the likelihood of theta by using this probabilistic Plackett-Luce model, which defines you a probability of your observed data. The observed data is just these rankings of different size, different subsets, for example, of red wines, for which you observe a ranking, and then you find the parameter vector which with the highest likelihood by likelihood maximization. Okay, so very quickly, my time is still 10 minutes, I think, is running. So let me just mention very quickly that instead of learning latent utility functions, what we can, of course, also try to do, especially if we observe pairwise comparisons as training data, is to learn preference relations. Once again, relations is one way to go to represent preferences. Utility functions, the other one. We could learn directly preference relations, and this naturally leads to, again, solving a binary classification problem. Our learner takes two alternatives as an input and predicts -1 or +1, depending on whether the first one is preferred to the second one or the other way around. Yeah, or maybe our learner gives a probabilistic prediction for this relationship. This can be done so this is not so difficult to do because it's a reduction to binary classification in a sense, and binary classifiers are well understood in machine learning, and there are many methods for doing that. The small problem with this approach is that if you train a binary classifier on pairs of examples of that kind, it is by no means clear that the relation that is induced by this binary classifier has those properties that we naturally would like to guarantee. Like, for example, reflexivity, antisymmetry, and transitivity of the predicted preference relation. So if you train just a binary classifier, it may easily happen that this classifier says or predicts that Y1 should be better than Y2, Y2 should be better than Y3, and Y3 should be better than Y1. And then you have a preferential cycle and don't know exactly how to obtain a ranking if you would like to have a ranking as a prediction in the end. And therefore, you have to think about how to deal with these problems, but in the interest of time, I will now skip this part and hurry a bit. I know this is not the best practice, but given the time constraints I have, I will also now skip this part about dyad ranking. This part about dyad ranking, actually, dyad ranking is a method that, or a problem setting, I should say, better, which combines both learning from label and learning from object preferences, in the sense that in dyad ranking, both the contexts and the choice alternatives are both represented in terms of properties, feature vectors. Yeah. So here you have feature descriptions on both sides. And the question is how to best make use of this feature information in order to learn a good predictive model. Again, the problem is ranking. Yeah, given a context rank a set, we would like to have a ranking of a subset of choice alternatives. So this is very much like in label ranking, but now the difference is that we do have this additional feature representation of the choice alternatives. Okay, I will rush over this part. And also only say very few, I know the rest of the things here I will only briefly comment on because I have only a couple of minutes left. For the model-based preference learning part, I anyway didn't prepare so much because I know that also Jerome was speaking about this. Just to remind you what I mean by this model-based learning methods is that you combine decision models which have been developed by people in the decision science, MCDA, MCDM, and so on, with machine learning methods, and these decision models that people have developed are often aggregation functions or aggregation operators, like, for example, the Choquet integral, which take as input individual ratings of, let's say, individual criteria, and combine them into an overall global utility of a choice alternative. And if you have training information providing you with information about these global utilities, or at least provide some hints at which one might be higher, which one might be lower, you may again tackle this as a learning problem and try to figure out the parameters of the aggregation function. So, for example, the parameters of the Choquet integral, the underlying capacity in the case of a Choquet integral. One important point, again, and yes, there have been many methods of that type, also considered in connection with machine learning methods, Choquet, Sugeno integral, generalized additive models, lexicographic orders, and so on. And these models are appealing because they have nice properties. Yeah, they are often interpretable. They guarantee nice properties such as monotonicity in individual criteria and so on. Okay, and one thing I wanted to mention is that from a machine learning point of view, again, one important thing is, or one important, let's say, prerequisite for learning is that you wrap these models into a probabilistic model, because these aggregation models or decision models are typically deterministic models, which, given ratings of individual criteria, deterministically determine global utility. But in practice, as I said, the data we observe in machine learning is often highly noisy and so on, and therefore we need to somehow wrap these models into a stochastic process, which we can use to explain the data we finally observe. Yeah, these could be models from discrete choice theory, which are often used here, and so on. And given such a probabilistic model of a data generating process, again, what we could leverage is learning principles such as maximum likelihood and so on. Okay. Now, I skip also this part, which is about online preference learning. Online meaning that, as opposed to the setting that I considered so far, which is a batch learning scenario, where the learner observes all the training data in a single batch, in a single big batch, and then learns a model from this batch of data, and then it makes predictions using this model. In online machine learning in general, and preference learning in particular, the data is coming step by step. It's coming in a sequence, and every time the learner makes a new observation, it updates its model, so it learns in an incremental way, and yeah, from time step to time step. So this is, of course, also quite important often in practice, because in practice this is often the case that the data comes step by step and is not given as one big batch beforehand. And okay, I will also skip this part, which is about learning choice functions, which is related also, of course, to the problem of ranking. But learning choice functions, the idea is that we are interested now not in a ranking function, which takes a subset of choice alternatives, for example, and delivers a ranking of these alternatives, but which now delivers a subset of preferred alternatives. So it chooses a subset of the good, so to say, the good choice alternatives. This is a related problem, of course, related to ranking, but not exactly the same. And we have also been working on this problem recently and developed methods such as what we call Pareto embedding, where we try to learn a mapping, an embedding of the choice alternatives into a space where the chosen alternatives are those objects which are Pareto optimal. Yeah. So in this way, you can encode, quite elegantly encode such a choice function. Okay, so then let me conclude. Not very much to conclude, actually, but I hope I convinced you that preference learning is an interesting and important branch of machine learning, especially because it has so many close connections to other fields, most notably, of course, the decision sciences. And as a research field, it's methodologically interesting, quite a number of theoretical challenges, practically useful and interdisciplinary. And this is what makes it so appealing from my perspective. Many things have already been done, but many open problems remain. And this is all I wanted to say, or I could say in the time constraints I had. So thank you very much for your attention.